This is Christine Johning in Lab M05 with my Lab 7 Black Hole Mass Lab Report. I used the information provided through WebAssign and altered the code from the in-lab portion to fit the current situation. The observation is the data of the star's position. The main result was that the mass of an unknown object can be determined based on the position of a known object due to the momentum principle and utilizing the position update process. This lab analyzes the rate of change of momentum and force to see how it affects the path of a star while in orbit, and analyzing the parallel and perpendicular components of each. Curve in motion is determined by the net force acting on the star, and how the change in position of the star according to the black hole affects the interaction of the force. This happens because the kissing circle decreases closer to the black hole. The component of the net force that is perpendicular to the momentum turns the momentum in a new direction. To make an object turn to the left, you must apply a force to the left. The perpendicular component of the net force points towards the center of the kissing circle. A bigger force implies a smaller radius of curvature, and a bigger momentum implies a larger radius of curvature. The component of the net force that is parallel to the momentum makes the momentum increase or decrease, and at a turning point it makes the direction reverse, but it cannot make the momentum turn to the left or to the right. Here is the information provided through WebAssign. It is important to save the document in a specific location to allow it to be called for in the program. Here is my code. The mass of the star is 1.989 times 10 to the 30th. Delta T is 60 times 60 times 24, or 86,400 seconds. The program called for the data from WebAssign. The code required the determination of the initial and final momentum vectors, the change in velocity and momentum, the net force, the parallel and perpendicular components of the net force, along with the parallel and perpendicular components of dp dt. It was then necessary to update the position and velocity and determine the path of the object. This is also where the code to find the position of the black hole and the mass of the black hole is located. The gravitational force equation states that the force due to gravity on object 2 by object 1 equals negative g times the mass of object 1 times the mass of object 2, divided by the magnitude of r squared, all multiplied by r hat. G is a constant equal to 6.7 times 10 to the negative 11th Newton meter squared divided by kilogram squared. 3 arrows were set up to represent the perpendicular net force in black, the parallel net force in blue, and the total net force in red. Here is the visualization. The model shows the elliptical path of the star's position. It also displays the black hole as a black dot on the screen. Predicting the path of the star allows the prediction of the mass of the black hole. The kissing circle can be larger than the path of the star, so the perpendicular force can be pointing out of the orbital path. The turning point is the point closest to the black hole. This demonstrates the time when the star changes directions. The new vector position of the black hole is predicted well if only gravity is acting on the object, and following the assumption that there are only 2 objects in the system, the star and the black hole. The new vector position of the black hole is predicted poorly if the system consists of objects other than the star and the black hole, since it does not take into effect their masses or gravitational forces on the force of the star. For the what does it mean question, delta P and delta T, and the delta P divided by net T, in other words, and the net force are in the same direction. Since delta P divided by delta T has the same value as the net force, the parallel and perpendicular components of delta P divided by delta T are equivalent to the parallel and perpendicular components of the net force respectively. The difference in the forces, perpendicular, parallel, and total, and the momentums, perpendicular, parallel, and total, is that a force is not able to be seen. A change in momentum, however, is visible because it shows the direction the star would be taking if it were not affected by any outside forces. Also, momentum and time can be measured in a lab environment, whereas the net force can only be inferred by using data. For the what if question, no, it is not possible to tell a difference in the replacement of the black hole. This is due to the fact that there cannot be a change in mass of the black hole without affecting the path of the star due to the gravitational equation. Thank you very much for watching my presentation.